Now in this video, we'll move into Unit 2, where we will introduce and discuss the trig functions, but only in right triangle situations. So Unit 1, we did a lot of discussion and we talked about angles in all situations, but now for this unit, kind of seems like there's a little bit of a disconnect, but then this unit, after we finish this, connects with almost everything from Unit 1 in Unit 3, where we'll discuss the trig functions at any angle. But again, we've got to get there. So in this unit, we have to start off by just discussing right triangles, basic facts. We'll get into the trig definitions. We are going to look at 6 trig functions. Some students have only seen 3 trig functions to this point. There are a lot of little problems that we're going to get through. There are a couple of identities. We're going to have to talk about some calculators, and then we will finish with applications, some like real word problems that use this type of information. So first things first, the right triangle. I'm going to draw just a random right triangle here. My right angle here. Now, one of the biggest things in a right angle is identifying the angle of concern. So, right angle has to be established, and then we have 2 other possibilities here, but it makes a very big difference if this is the angle we care about or this is. So let's use this for this first problem. I'll just put in a little theta down in this corner. So there's my theta. And now with this basic setup, now I could change the angle and everything, and we'll play some games with that in just a moment. But with this basic setup, the side directly across from the right angle, we call the hypotenuse, and we'll just call that H for short. The side directly across from the angle that we marked, so again, if this was the angle we marked, this would be the side, but with this being the angle we marked, this is the side. This is the opposite side. We use O for opposite. And then this last side, this third side, is the adjacent side. And we use A for adjacent. The adjacent side is the side that connects to angle theta that is not the hypotenuse. But for most people, they just do it the same way we did. You identify the opposite and hypotenuse. Those are quick and easy. And the adjacent is the third side. But 2 quick things. Number 1 is let's just draw a different right triangle. Let's put theta up here inside of this right triangle. With this setup, that would be my hypotenuse. This would be my opposite. And then that would be my adjacent. But now, I actually don't like that our book did this so quickly, because most of the time when we're dealing with a right triangle, there's really just one angle that we care about, so let's just focus on that. But we should be clear, and I want to do similar to what the book did. I want to use a different color pen to establish this last little idea. So I'm going to draw one more right triangle, and I'm just going to change the orientation again, so that part doesn't matter. So now one more right triangle. I mean, it's kind of similar to this one in the position of the right angle. I'm just exaggerating the sides a little more, but that's not the key point. This is always going to be the hypotenuse, but what angle do we care about? I'm going to use alpha down in this angle in this corner, and I'm going to use beta up here in this corner. Oops, I'm sorry, I wanted a different color. Let's use beta. Let's do beta in red. Both, this doesn't matter which angle we care about. This is the side across from the right angle. So this is H in either situation. But if alpha is the side we care about, this would be the opposite and this would be the adjacent. If beta is the angle we care about, then this would be the opposite and this would be the adjacent. So the first point here is a lot of students make a right triangle, and the hypotenuse they normally do well with. But what is opposite, what is adjacent? It definitely comes down to which is the angle of concern. So it's just, you can't just quickly say, well, this is opposite adjacent. Well, that's a setup if this is the angle you care about. But if this is the angle you care about, then this is the opposite and this is the adjacent. So again, I'm really trying to stress, don't forget the angle. People ignore this part and then they can sometimes get in trouble because they flip-flop these values. Okay, that's the first part. That's just the introduction to the right triangle. Technically in the book, that was 2.1. No problems yet. 2.2, we jump right into what are the actual trig definitions. Now, trig functions, I'm going to write them out in full, talk about their abbreviation. So we have what most people consider the three primary trig functions: sine, cosine, and tangent. And that's where most people, at least to some extent, you've seen those. As we mentioned on the calculator, no matter which calculator, you got a sine, cosine, tangent button. That's what you need for this class. And again, some people think it stops there, but there are three more trig functions. We also have cosecant, secant, and cotangent. This is another one of those spots where, you know, there are just so many different things you can memorize. There are so many different charts and all these little things you can do, but it's so more important to understand the right things. So first things first, let's get the abbreviations. This is the full name. Now we'll get the abbreviation. Sin of theta. You need this extra part, okay? Sine of theta. Similar with all of them, all the abbreviations. Sin for sine, cos for cosine, but then you need the theta. Tan for tangent, still need the theta. CSC. This is a huge one where for some reason people like to take a 5-letter abbreviation and write cosec. That's not the abbreviation. It is just CSC. That's the abbreviation for cosecant. SEC for secant. And COT for cotangent. But as I keep suggesting, people have bad habits where they don't include. It's not always angle theta. Maybe it's alpha, beta. But every time you write the abbreviation, there needs to be something, some argument that goes with each trig function. So you never just write the letters SIN by themselves. That's garbage. It's got to be sine of either a generic angle, sine of theta. Maybe we'll just use a regular x, sine of x. Maybe it's a specific angle, sine of 30 degrees, sine of 2 pi over 3 radians, right? But every time, and it's not just sine, it's all the others, you need to have both the abbreviation for the trig function and the angle to go with it. Whether the angle is a variable or it's a specific value, degrees, radians, it has to have that second component. Now, with that setup, we've got our angle. Now we get the definition. Sine of theta is the opposite side over the hypotenuse. Cosine of theta is the adjacent side over the hypotenuse. I'm already just abbreviating, right? I've already established what O, H, and A all stand for, so I'm just using those right here. For some people, if you don't already know these things, you know, part of memorization, if you write it all out, that'll help you memorize it as a fact. In this class, you'll always be able to refer back to your charts, but again, thinking about moving forward, if you have a physics class that follows, you're probably going to have to memorize some of these values, so just, you know, writing it out is a good memorization technique. But the abbreviations when you're ready. Tangent is opposite over adjacent. Now, the book keeps going. The book then starts describing the other 3 remaining trig functions. They start giving us that cosecant is the hypotenuse over the opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. All of this, I'll just make a quick note, this is all page 27 in your book. But I strongly recommend thinking of this instead. This is where, again, let's memorize the right facts and understand how to use them instead of memorizing just page after page, table after table of facts. Those are the definitions we need. I initially started off saying these are three primary trig functions. These are technically these are the reciprocal trig functions. And they're the reciprocal because cosecant is the reciprocal of sine. 1 over sine gives you cosecant. Secant is the reciprocal of cosine. 1 over cosine gives you secant. And cotangent is the reciprocal of tangent. This is the smarter thing to memorize because this 1 over, let's just do some quick math for a minute. Let's say you knew sine of theta is 2/7. So that will be a given fact. Cosecant of theta, well, that will be 1 over 2/7. But cleaning up answers like this is an improper fraction, but dividing fractions is multiplying by the reciprocal. So 1 divided by 2/7 becomes 1 times 7 over 2, and you're multiplying by 1. So that action ends up just flipping the value. So if sine is 2 over 7, cosecant is 7 over 2, and you could do this vice versa. If you started off knowing cosecant was 7 over 2, you flip that. That's the reciprocal, everybody. That's what the reciprocal means, 1 over. And when you do a specific 1 over, it just flips your fraction. So that's easier. Instead of, that's going to come up later on in our book, but that comes up as a second fact about these functions. But why not get that right off the bat? That's what we need. And if we ever needed the right triangle, well, then we could do it. If 1 over sine is cosecant, well, 1 over opposite over hypotenuse, just like 1 over 2/7 flipped to become 7 over 2, 1 over O over H becomes H over O. So I'm not even going to write that out because I don't think you should memorize that. You should understand this to be able to use that fact. But now, second thing, I said these are the three primary. Actuality, these are the real primary. Tangent just comes up often enough that it gets lumped in with these two, but really sine and cosine are the key to trig. Everything can break down to sine and cosine. Tangent, for instance, again, another fact we'll learn later, but let's just get to it right now. The book will bring this up later. Tangent, an alternative, in addition to the opposite over adjacent, can also be written as sine over cosine. So now, looking at that, and now let's extend that. Well, if 1 over tangent, well, if tangent is sine over cosine, 1 over sine over cosine becomes cosine over sine. That is crucial, everybody. What we are establishing right now is that even though there are 6 trig functions, there's really 2 trig functions, and the remaining 4 can always be rewritten in terms of those original 2. Okay? So right triangles come up a lot, and we'll see, get some plenty of practice with those problems. Technically, as long as we can get sine and cosine from those right triangles, we can get every other trig value. But again, tangent does come up often enough. It's also worth memorizing this as an extra component. And then, again, as tangent comes up a lot, 1 over tangent may sometimes be helpful, but sometimes we still need to get back to sines and cosines, so we'd use this. Last little piece, and now we'll actually start getting to work. Let's start doing some problems. Let's start seeing how we use this information, how we could manipulate, be given one piece of information to try and find another. We've got several things that we need to talk about. Oh, and one very quick thing I should have mentioned right back in the beginning. We established these 3 sides of a right triangle in all these different situations, but the other thing not to forget is in a right triangle, we could also apply Pythagorean Theorem. And a lot of people, they say Pythagorean Theorem, they think of the old a squared plus b squared equals c squared. That's fine. That's a perfectly fine way to memorize it. Just recognize in Pythagorean Theorem, c is the hypotenuse. So some people like to, this works fine, and plenty of people know it this way. Just always remember the hypotenuse has to be the side by itself. And whether this is side A and this is side B, or this is B and this is A, you know, that doesn't really matter as far as applying Pythagorean theorem. Which is the opposite, which is the adjacent, that makes a big difference when applying the trig functions. But as far as this little equation using Pythagorean theorem, that won't make a difference. Okay, so let's start off with a simple problem. I give you this right triangle. Our book always says these triangles are not drawn to scale, so there's never any exercise in trying to measure this out. So again, I just made these up and I threw these values in. You've got this full right triangle. Let's find all the trig values at angle theta. Now, here's just one quick thing I should mention. We will use calculators in this unit, but find all the trig values. We're going to start seeing this exact answers only. We're going to see that type of notation. When it says that in our directions, that is basically telling us don't use your calculator. Because there are some people who already know some little tricks and how calculators can help, but calculators will give us decimal approximations. When we get to word problems, that's what we're going to need. But if you just try and use your calculator too much, you're going to be missing some of these directions, and it's going to cost you on some of our quizzes and final. So again, make sure you're doing things the same way we are to make sure you're establishing the right ideas and that you're following the directions properly. So this one, find all the trig functions at theta. Well, it's just an exercise of using all this information up here. I just need to look at my triangle and go over here and say, okay, well, from theta's perspective, sorry, right here, from theta's perspective, the opposite side would be 4. The hypotenuse, there's the side that's across from the right angle. Therefore, 3 must be your adjacent side. So, well, how does that help? Now we just follow our definitions. Sine of theta, O over H, opposite over hypotenuse, will give you 4 over 5. Again, everybody, know yourself. If you are kind of familiar with this, maybe just doing some quick labels and you could just refer back, that's fine. But if you're still just getting used to these definitions, write it out. Don't just jump to the answer. Label your sides, write out the definition, sine is opposite over hypotenuse, then get your answer. Those little things you do now in your homework as you go through, do the problems in the video, going through the book, doing those problems, getting good habits now, doing those little extra things now will really help for those classes later on when you may need that. Like I said, whether that's a pre-calc or a physics class, whatever, you know, even pre-calc, I should point out, they expect that you already know a lot of these basics. So it's one thing to just need a few reminders. It's a complete different situation if you never really established a lot of these good habits. Okay, before I keep going, let me point out something that's wrong. Garbage. And it looks innocent. And people are like, well, what's wrong? No, it's the same thing. You're missing the theta. And that is so crucial. Because if you honestly did this, what that would really lead you, if your reader really tried to give you the benefit of the doubt, you never labeled your angle. So they would be looking up here. This is the unlabeled angle. And from this angle's perspective, 3 should be the opposite, not 4. So again, that's not something trivial. Besides the fact that doesn't make any mathematical sense, that you need the trig function of the angle. I mean, I should point that out. What are trig functions really? At this basic level, they are the ratios of the sides. But those ratios, those sides, depend on which angle you're using as your point of perspective. So that's why we need to have the full establishment. Trig function, angle we care about, and now we look, okay, opposite over hypotenuse, there's our answer. Next, I'm just going to go in order. And that's the second thing, everybody. Sometimes being a creature of habit really helps. Sine followed by cosine. Well, cosine adjacent over hypotenuse. 3 over 5. Technically, you could do tangent. Use this piece. Tangent is 4 over 5 over 3 over 5. But again, you know, exact answers, but we also want reduced clean fractions. So just like this, that was technically correct, but we don't leave an answer 1 over 2/7. We flip it and get 7 over 2. So if you did do this the little bit of the long way, you have 4/5 over 3/5. Continue that. That becomes 4/5 times 5/3. 5s cancel, and you get 4/3. But of course, that, we had sine and cosine, plug those in, reduce, clean it up a little bit, or just jump right to the right triangle, opposite over adjacent, there's your 4/3. And now the last three, again, look at the order. I know a lot of people really like to group cosine and cosecant together, and they both start with co, they both have the C designation, whereas sine and secant both have the S, but that's not the way they're paired. Cosecant is 1 over sine. Secant is 1 over cosine. It's like each one of the primaries, it has a pairing with one of the others, but a non-co goes with a co goes with a non-co goes with a co. I mean, there's little things some people try and use to help connect which one of these goes with which one of these, but sometimes, again, just being a creature of habit. Sine came first, now cosecant comes first, cosecant goes with sine. Cosecant 1 over sine, so that would flip, and we get 5 over 4. Secant is 1 over cosine, so 1 over 3/5 becomes 5/3, and cotangent, and here I can keep flipping, but let's just use the 1 over tangent. If tangent is 4/3, then 1 over 4/3 cotangent would be 3/4. One last thing, I want to do a couple more problems. This one, I started you off with the whole right triangle and then we jumped in. So we want to play a few more games, get more practice, establish a few more little ideas here. But just before we do that, let's come back up here for one more moment. These, like I keep suggesting, I did not need the right triangle pieces. I just went in order, I found these, and then it was very easy to follow up and then have these. And I strongly recommend that as a good practice to follow. And like I also pointed out, you could also do some flip-flopping if you needed to. But for later problems, if we knew this in the first place, well, the same way 1 over this gives you this, vice versa, 1 over this gives you this. So that flip-flopping goes in both directions. 1 over 4/5 gives you 5/4. 1 over 5/4 gives you 4 over 5. But when it comes to the sides of the triangle and these three primary trig functions, there's a little acronym that a lot of people like. Sohcahtoa. Now, that's a bit of a mouthful. But first, what is Sohcahtoa supposed to actually do for you? What it's supposed to be establishing for you is the trig function and then the two sides in order how they all come together. So it's really three pieces here. So is the first piece, which tells me sine becomes opposite over hypotenuse. Again, go from top to bottom when you make your fraction. So sine equals opposite over hypotenuse. Then next, the co part, cosine, C is cosine, goes to adjacent over hypotenuse. And then last, the toa, tangent, is opposite over adjacent. That for some people is gold, because this is such an important established relationship for the trig functions. Again, this gets used a lot going through the rest of Unit 2, Unit 3, Unit 4, Unit 5. You want to go in, like I said, physics. Most of physics, you need the right triangle trig, and there it is. You go into pre-calculus, well, you need more, but the basics of trig, and there it is. So that is such an important idea. But here's the catch, everybody. For me personally, I didn't spell Sohcahtoa correctly until I already knew this relationship. You know, people say so, but they forget the H. Ka, you know, is that an A? They go C-O-H. There's so many little mistakes people make when they try and spell out Sohcahtoa. So again, just realize, if you're going to use that, make sure you're putting that together and that you understand how it's actually being used. Okay, so let's move along here, and let's move into a next problem. Let's say we start off given cosine of theta equals 5/6, and theta is an acute angle. All this is given information, and now here's my directions. Let's find the remaining trig functions at angle theta. Okay, so how do we make this work? It's not too bad, okay? First thing is, why am I putting this extra part that theta is an acute angle? To be quite honest, that's kind of covering us for when we get to Unit 3. And we'll come back and do the same problem and point out why that is important. So for right now, it's kind of like you could ignore this and focus on this. How the heck am I supposed to find the remaining trig functions if I only know one? But here's the key, everybody. Once you know one trig function, you could always work a little bit backwards, make the right triangle that goes with it, and then turn the rest of the problem into this one. So use this information. How am I supposed to use this information? Well, it's cosine. So I know cosine is adjacent over hypotenuse. Therefore, I know the adjacent side has length 5 and the hypotenuse side has length 6. Now, I'm not, like I keep saying, I'm not using right triangles for any scale. I'm just doing it to just establish the correct sides. So I'm going to tuck my theta into this corner, and I'm going to make a right triangle based off of this information. Well, this would be the hypotenuse side, so my 6 would go here. This would be the adjacent side, so a 5 will go here. But I'm missing the opposite side. But that's okay. As long as, again, this is not all triangles, but for right triangles, and that's what goes hand in hand with the trig functions here, right triangles, we've got Pythagorean Theorem, and this is what I was trying to talk about earlier. When people are missing a side in a right triangle, it is a very, very common mistake for people to do this. They just take the two sides they know, that squared plus that squared equals the unknown squared. But that, I mean, sometimes you might get lucky, but that is incorrect for this problem. Because as we said, the hypotenuse always has to be the side by itself. So whether you go blank squared plus 5 squared equals 6 squared, or if you reverse these, 5 squared plus blank squared, that's fine either way. But it has to be that the hypotenuse is the side by itself. Now, when we solve this, we get 36 here, 25 here. I'm just a little short on room here. It's no problem if you want to write it out. 36, 25, subtract the 25, you get 11. Technically, you take the square root and you get plus or minus, but we're using this as distance. So we're not going to put negatives here. We'll just get from this that the opposite side is the square root of 11. Now, some people would look at that and say, little things, can we do better? Well, one thing, we don't want the calculator. That's where people come up here and like, why did he make the big deal about exact answers only? You know, it's very easy for a calculator, if you get a calculator answer of 0.8, to convert that backwards and get the fraction 4/5. And similar, even something like this one, where 5/3, you would get 1.66666 forever. But there's still ways people understand and calculators can handle some back and forth. But here, we don't want the decimal approximate. That's part of the exact answers. Don't go to your calculator and go, okay, well, the square root of 11, and you get your 3.3, whatever. You're rounding off. that goes forever. Once you cut off, you're rounding off. That's an approximate. That's why we're establishing this exact answers, so that we leave that alone. That is the square root of 11. The only thing we would say is if we got something, like if we got the square root of 20. Let's just pretend for a moment that we got that as our third side. It's not a perfect square. I mean, if we get a perfect square, right, the square root of 25 is 5. That's great. Don't even hesitate with that. But if it's not a perfect square, but it has a perfect square as a factor, like 20 is 4 times 5, don't forget that little bit of cleanup here. The book will definitely do that as a part of its answers. If you forget to do that on a quiz or a test, that's going to be a minor mistake, like a -1 at most. But it's still a good habit that we want to get into. But 11, geez, 11 is prime, and it's not even that it's prime. It has no factors that are perfect squares, so that's as good as we're going to get. And now realize all these little steps, and now we're in the same situation we were here. We took this information, started a right triangle, needed Pythagorean theorem to finish the right triangle, but now we've got it all put together, so now we can finish. Now we can go through sine of theta, opposite over hypotenuse. We get the square root of 11 over 6. We already had cosine. Doesn't hurt if you list it again. I'll just do it just to keep them all together. Like I said, some people, that be a creature of habit thing can really work well for them. So even though you already had cosine, you still do the 3 primary in order. Not that these have to be the order, it's just the order that most people go through and do them. Tangent, and that's the order, by the way, because that's the order Sohcahtoa is read. Now we're up to tangent, so opposite over adjacent. Now when we go to the reciprocal, cosecant, this flips, but here's the next catch. The book, good habits, we don't like radicals in the denominator. So this is a perfectly good answer. I might give you a little bit of a hard time if you don't reduce a radical, and it could. I really want to give you a hard time here, but it's still a good habit. Don't leave the radical in the denominator. How do you get rid of it? You do this rationalization technique, because rad 11 times rad 11 is plane 11. The square root cancels. Sorry, that's a little messy. That's 6 square root 11 over 11. That's the final answer for cosecant. Nothing troubling with secant. 1 over cosine, we just get 6 over 5. But then cotangent, we flip, we get 5 over radical 11. And then similar, rad 11 over rad 11. So we get 5 radical 11 over 11. And those are our best answers. Okay, one more like this. Almost the same thing. Let's start off. This time, let's start off with cotangent. And let's look at cotangent as radical 7 over 3. And same thing, theta is acute, is an acute angle. Find exact values for the remaining trig. Now, the previous one, I started you with cosine. So a lot of people, it was a little bit easier. Oh yeah, cosine we know, adjacent and hypotenuse. Again, already getting used to or already accustomed to using Sohcahtoa and these basic relationships. But this is what I was just telling you a moment ago. Before, if you have the other ones, get it back to what you need. So with that as your starting spot, then we equally know tangent of theta is 3 over radical 7. Now, when I get to my final answers, I'll clean that up some, but for just making the right triangle, use that. That means 3 is the opposite side, radical 7 is the adjacent side, so I can make a right triangle. Again, you're making the right triangle just like I am, so If I get the choice, I make that same first right triangle every time. So that way, if I get to make it, I just very quick, opposite, adjacent, hypotenuse, theta in that bottom corner, so all of that matches. And that same thing, I don't care about what these measurements actually are. The opposite side is the 3. The adjacent is the radical 7. But now this time it is the hypotenuse that is missing. That's why I didn't say it's always wrong to put the unknown by itself. You have to actually look and see, and that is what happens here. 3 squared plus radical 7 squared equals, well, here I have it as h. Before I used a question mark. Again, that's fine, however you want to do it. This is just the work getting us ready for our answers. So if we have little variations, there's nothing wrong with that. If you go back for one quick moment, go back here. Look how all these are nice whole numbers. And there's definitely an example like this in the book too. It happens. There are these things that are called Pythagorean triples, where when you go through Pythagorean theorem, 3 squared is 9, 4 squared is 16. Add those together, you get 25, which is that perfect square. But we can't expect that, everybody. So that didn't happen here. That third side ended up being a radical. Here, well, I started off with one of my sides as a radical. So what happens here? I don't know. Anything can happen. Let's see. Well, this one, 3 squared is 9. Rad 7 squared is 7. This one happens to work out pretty nice. Again, technically we get plus or minus 4. But again, we're thinking of these as distances, so we're not going to use any negatives. So we'll just keep the 4. So it really is. It's just like the previous one, just that I started you one extra step further away. And that's what I was saying earlier. You just try and grab a calculator. There's a lot of random button pushing, and you may get some nice answers and others. Maybe your calculator does some nice conversions for you from some of these ugly decimals. I've never seen a calculator that can take this decimal and tell its user that really boils down to the square root of 11 over 6. It may be able to do it for a nicer fraction like this, but not one like this. So again, we may use our calculator for little bits of the computation, but we're really not using any of the sine, cosine, tangent buttons here, trying to get used to the right triangle relationships. So all this, that should have been the hard part, and now we're on the easy part. So sine, opposite over hypotenuse, 3/4, cosine, adjacent over hypotenuse, rad 7 over 4, tangent. Well, again, we already had it, but this is a nice place that some people just like to confirm. If we made any little goofs, maybe we accidentally put something in the wrong spot, we better get this, and it does work. Opposite over adjacent. And I rationalized. And then I'm going to run out of room in the corner, so I'll just keep going down. Cosecant. And notice even how I read it. I just said sine equals 3/4, but you still have to include the theta. Even if you just read it quick and people understand, it's a very common thing to do, but to get full credit, you gotta have that theta in there. So we keep going, cosecant of theta, well, 1 over this, that flips, we get 4/3. Secant of theta, 1 over this, we get 4 over radical 7, but we'll clean that one up. And then last, cotangent. Well, again, we had that. But here's one quick tip, everybody. Let's pretend we were just going to, we had this value, so we're going to flip it. If you already had to rationalize, don't go to the rationalized answer and flip. Go to the one before. You flip this, you got to rationalize all over again. You go back and flip this one, and you just get a nice, quick final answer. Okay, so a lot of good right triangle problems. We've gotten a lot established. We still have a few more pieces that need to go with this. Next piece, I want to do a triangle where we're looking at 2 angles at the same time. Okay, so let's draw a new triangle. Let's put alpha up in this corner, beta down in this corner, And let's get some values. Let's stick to another nice situation. Let's go 6, 8, 10. And let's start doing a few things. Let's start with, let's evaluate all the trig at alpha, and then we'll separately do all that for beta. So sine alpha, I'm going to go a little fast here, everybody. Take your time if you want to, pause the video, take a moment, focus on alpha, get your sides established, get all your values, then do the same thing for beta. But I'm going to go through this a little more quickly because this is going to lead to our next, it's a little point. The right triangle is without a doubt our biggest thing for right now, but we got to make a few other little connections. So let's go through this from alpha's perspective, 8 over 10, which I can reduce to 4 over 5. Cosine of alpha, adjacent over hypotenuse. Oops, tangent next. Tangent, opposite over adjacent. And then the other three, cosecant alpha. Flip this, secant alpha. Flip this, and cotangent alpha, flip this. Now, like I said, I went pretty quick, so just take your time, make sure you confirm you get all the same things. Now let's take a look at beta. Sine beta, now this is the main angle, so now that's opposite hypotenuse. Hypotenuse doesn't change. 6 over 10, 3/5. Cosine beta, beta, adjacent over hypotenuse, 8 over 10, which is 4/5. Tan beta, opposite over adjacent, 6 over 8, which is 3/4. And now the reciprocals, cosecant of beta will be 5 over 3rds. Secant of beta will be 5 over 4. And cotangent of beta will be 4 over 3. There is an exercise in the book, this is one of the first ones, example 20, that they start you off by doing almost this exact thing, but then they kind of try and lead you a little bit to what do you see? And what they're trying to get you to realize is that cosine of alpha and sine of beta, or sine of alpha and sine of beta, sine of alpha and cosine of beta, sorry, that's the same thing. That's the same thing. And then notice, tangent of alpha, cotangent of beta. Cotangent of alpha, tangent of beta. Those are the same thing. I'm not saying all four are the same. I'm saying together, right? Tangent of alpha is the same as cotangent of beta. Or cotangent of alpha is the same as tangent of beta. And the same thing with cosecant and secant. Cosecant of alpha, same as secant of beta. Secant of alpha, same thing as cosecant of beta. So I really don't want this to look like all these. It's just these, this goes with this, and this goes with this. Like these up here, and like these down here. This is what we call the cofunctions. That there's an established formula that sine of theta is always equal to cosine of 90 minus theta. Or vice versa, cosine of theta is equal to sine of 90 minus theta. That is always, always how it will work. And I could do the same thing with the others. Tangent of theta is the same as cotangent of 90 minus theta. Or vice versa, cotangent of theta is the same as tangent of 90 minus theta. Cosecant of theta, same as secant of 90 minus theta. And secant of theta, same as cosecant of 90 minus theta. Go back to the very definition. Why are they called cofunctions? And why are they pairing in this way? Well, look at their actual words. Sine, cosine. Tangent, cotangent. Secant, cosecant. That's how you know the cofunctions what functions are cofunctions with each other, just remove the co if it has it or add the co if it doesn't, and that's how you pair them. So it's one of those really interesting properties. Why does it work that way? It's because it's all based on a right triangle. What is the value of angle alpha? Well, if you know angle beta, let's put some actual numbers in here. If I knew beta is 60, well, all three angles in a triangle, not just a right triangle, but in any triangle, the sum of the three interior angles adds to 180. But now, since we're always dealing with right triangles, we know we've used up 90 degrees right here, so you have 90 degrees for these two to share. So by writing 90 minus alpha, or 90 minus theta, if this is theta, then this is 90 minus theta. That will always work out with those two interior angles. And why do these relationships work like that? Well, that goes back to what we pointed out in the very beginning. If this is the angle you care about, well, that's the opposite, that's the adjacent. But if this is the angle you care about, those two sides flip. So that's the connection why all these things happen. I actually feel our book makes a little too big of a deal of that. I mean, they really ask a lot of questions. It's nice, but that's really all I want to say. It's nice to point that out, but it's not like it's any groundbreaking, super useful aspect. It's helpful. It could work in some situations, but it's not as amazing as it may first seem. Okay, so we've got two more little pieces here. Because now we've got all of our nice pieces established, but now we need to start talking about special triangles. And this is going to be another one of those places I'm going to go right from the beginning. Start from the beginning, work our way through, but really it's going to lead to like one nice final conclusion. So our special triangles, we are going to look at a triangle that has 45-degree measures in it, and then a triangle that has 30 and 60 degrees in it. And what we're ultimately going to want to do, this is another one of those things. The book kind of hints, but then leaves you hanging a little bit, but I want to make it clear right now. After we do this, we are going to be able to fill in this nice little reference angle chart for these very special reference angles. We'll focus on these three for right now. I'll fill in these two just to complete the chart so we have it. But again, 4.3 is where we'll see where these even make sense. How do you have an angle of 0 degrees in a right triangle? That doesn't really make any sense at this point. But in Unit 3, when we look at trig functions at any angle and go back to thinking about that whole standard angle and our 4 quadrants, we'll see how those fit in. So let's start off. It's funny, I'm talking about special triangles, but I'm actually going to start off with a square. If I have a square, all sides length 1. Now, what do I do with that square? Doesn't matter which diagonal, but introduce a diagonal. And now you've just made a right triangle. And because this was a square, this diagonal also bisects the angle. So you're bisecting a 90-degree angle, meaning you're getting 45 here and 45 here. We use a little Pythagorean theorem. 1 squared plus 1 squared equals the hypotenuse squared. And we get the square root of 2 for the hypotenuse. Why are we doing that? Well, we're setting that up so that we can find sine and cosine at 45 degrees. Again, I'm going to come back and make this whole chart in a moment. But other people, instead of this chart, it's like they memorize how to construct these triangles. Again, it's fine, but then that means there's several triangles you have to memorize. And again, just not quite ideal. Oh, another thing, I'm establishing all of these in degrees. We should definitely also recognize them in radians. If you haven't done enough radian practice, I mean, definitely you should be able to do that without much trouble. 30 degrees, either now you could just confirm now that I filled them in, that pi over 6 works. 180 divided by 6 is 30. but you should definitely be able to see and make that conversion yourself. But now that we have this set up, it's easy. Doesn't matter which 45, use this one, sine, opposite, over hypotenuse, which when we rationalize will look like that. And cosine, well, from this it would be adjacent over hypotenuse. And notice again, I used this angle, but it didn't matter if I did this one. This one for sine, opposite over hypotenuse, same thing. And then this one, adjacent over hypotenuse, same thing. So those values will fill in here in just a few moments. And you may say, well, wait a second, what about the other trig functions? But that's why I pointed out all the other trig functions. We're not going to get a lot of practice with this now. This comes up a lot in 4.3, but once you know sine and cosine, you can get any of the others. How do you get tangent at 45? This divided by this equals 1. How do you get cosecant of 45? You do 1 over this and you get radical 2. So again, this is still such an integral part. Right triangles, we definitely need the relationship, but for the other trig functions, knowing how to connect them to sine and cosine. Okay, so there's our 45. That's one special triangle. The second one, I mean, they also in the book point out that if you do this a little differently, like if you want all these to be side length 2, well then this becomes 2 radical 2, and when you reduce your fractions, you get the exact same thing. So there's nothing special about me picking that these were all side length 1. No matter what side length I pick, the ratio, that's what it's all about, everybody. These will end up being similar triangles, and similar triangles, the ratios of the sides are always in the same proportion. So the trig values would be the same thing because the trig values represent those same ratios. Okay, so moving on. Now let's set up this as my follow-up picture. And this is supposed to be an equilateral triangle. So equilateral, all sides are the same length, all angles are the same. So if all angles are the same, these would all be 60-degree angles. They'll have to add to 180, but they're all the same measure, so they're each 60 degrees. And for this one, I'm going to make all side lengths 2 units each. So it's kind of like a weird start, just like this one. But after I introduce this diagonal, then we had a right triangle, and that's ultimately what we cared about. Similar, but not quite the same here. Here, instead of a, there's no diagonal here, but I will drop a perpendicular bisector, which again, because it's a special triangle, not only does it hit this at a 90-degree angle, it just cut this in half. So instead of here to here being 2, just here to here would be 1. And it cut this angle in half, so half of 60, 30 degrees here, 30 degrees here. So now that's the triangle I care about. Little Pythagorean theorem. This time it's not the hypotenuse we're missing. 1 squared plus blank squared equals 2 squared. We'll get that missing side is the square root of 3. And now, let's start with 30, and then we'll do 60. This triangle will take care of both of those special angles. From 30 degrees perspective, sine, opposite, over hypotenuse. Sine of 30 is 1/2. Cosine, adjacent, over hypotenuse. And that will give us the square root of 3 over 2. And now 60, from 60's perspective, sine, opposite, over hypotenuse. Gives you the square root of 3 over 2. And then for cosine, adjacent over hypotenuse, 1/2. This is another spot I could use that cofunction. Sine of 30 is equal to cosine of 90 minus 30, which is 60, and vice versa here. But again, it was just easy enough that we have the triangle to just look at the triangle and get those full results. So I could fill these values in. 1/2 here, radical 2 over 2 here, radical 3 over 2 here, and then basically same values but opposite order. But watch this little trick, everybody. Again, this chart is going to be very helpful moving forward. And a nice way to make this chart, make sure you get all your angles and make sure you start with sine. Everything starts divided by 2, and then in your numerator, under 0, you start with the square root of 0. The square root is just in the numerator, not the whole fraction. And then in the next box, add 1 under the radical. Then add 1 again, then add 1 again, then add 1 again. I just keep adding 1 under the radical as I move to each subsequent box. And the last thing I'll do is clean these values up, the ones that I can. The square root of 0 is 0. 0 divided by 2 is 0. The square root of 1 is 1, so that just becomes 1/2. Radical 2 doesn't get any better, so that stays radical 2 over 2. Radical 3 doesn't get any better, stays radical 3 over 2. Radical 4 is 2, and 2 over 2 is 1. Those 5 values, those are the values of sine at these 5 very specific angles. And now for cosine, again, I could do the cofunction idea or just realize same answers but reverse. And I don't have to start the whole process. As long as I've already cleaned up the answers here, just reverse it. Start with the 1. Then next comes the radical 3 over 2, then the radical 2 over 2, then the 1/2, and then the 0. Okay, so we get that established here. And in the book, they ask you a few questions just to, try and get you to practice. So what is cosecant of pi over 3? Well, it's 1 over sine of pi over 3, so you get 2 over it. They give you a few problems just to try and get you to practice that a little bit. But now, this is where we really get to the last big piece. Yep, the last big piece, and then we'll finish this with some word problems and see how calculators can help. But notice, this video, we're just about at an hour here, and outside of just some basic arithmetic, I haven't used my calculator for anything. So, like I said, make sure you're following exact answers, getting used to what they're trying to get you to do, so you're not just getting good answers, but you're also following the directions to get full credit for all problems. So, the last thing we have to discuss, this is section 2.3 in the book, the Pythagorean Identity. We already have seen the Pythagorean Theorem, and we've used it several times now, all these right triangles, and anytime we know 2 sides and are looking for the other, that's exactly what we've been going to. But now let's take a look at this. Realize that in this setup, oops, sorry, I wanted to draw my regular one, so right angle here, there's my theta, there's A, there's B, there's C. And if you want to flip-flop A and B, that's fine, but the big key is that C is the hypotenuse. Let's divide everything by C squared here. I get A squared over C squared, which is the same as A over C, quantity squared. B squared over C squared, B over C, quantity squared. And then C squared over C squared, well, that cancels and you get 1. Why am I rewriting Pythagorean theorem like this? Well, I'm doing it with this right triangle here so we could see A over C represents the sine function. So A over C squared became sine squared. And here's one little side note, just good habits and everything. When you're squaring a trig function, don't put it like this. That would be understood that you're squaring the angle on the trig function and then applying the trig itself. If you want to do it this way, you have to use parentheses to make that clear. There would be situations, we won't see it in this class, but for those who go to pre-calc, that square on theta makes more sense. I mean, it should make sense just as far as functions if you think about it. Of course, just like anything else, we don't always just use variable x. Variable x could be squared or cubed or anything like that. But that's the proper way to do it with your notation to make it clear. It's the trig function that's being squared, not the angle. But the better way, and the way every textbook writes it, is this way. You put the square next to the trig function with the angle after it to make that clear. Okay, similar here. B over C, adjacent over hypotenuse, that would be cosine, and that is also being squared, and that equals 1. That is the Pythagorean trig identity. Again, we'll see a quick use for it in just a moment. That'll be the last piece of this video, will be the use of this, and then I'll point out a quick alternative. But for those moving forward, that is enormous. That is such a big identity that gets used over and over in pre-calculus and calculus. For math people who keep going, that is such an important thing to remember. And that's only the first Pythagorean identity, because now, if you remember all of our basic trig definitions, take this whole equation, let's divide everything by cosine squared. Sine squared divided by cosine squared would be tangent squared, plus cosine squared divided by cosine squared would be 1, and then 1 divided by cosine squared would be secant squared. There's the second. It's just a little alteration off of this equation. Here, I actually prove that. It doesn't look like much of a proof, but that is truly a proof. And here, I just manipulated it, and I didn't do anything wrong. I just divided and made sure I divided everything. And now I'm going to come back up to here, to the original, and if I divide by sine squared, what happens? Well, sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared. Even in pre-calc, like this is a must. These can always be figured out in the same way I just did, or there's some other little tricks some people remember. But that's the key that most people are not going to remember the proof for. But once you have that established, again, just the two primary trig functions. Divide by each one at a time, the square of each one at a time, and you get these reciprocal identities. I mean, this is not a reciprocal function, but that's where people, they call it that because of the other reciprocal trig functions. Okay, now, I still want to use this, but I just want to point out on page 37, you get, I mean, it's not just these Pythagorean identities, you get a whole bunch of stuff. It's a nice big full table of pretty much everything we established and more. You know, we get the reciprocal pieces. They already had a separate table for the Sohcahtoa. They don't include that. But then you get the reciprocals. Then they get all the cofunction stuff that we talked about. Then they put all the Pythagorean identities. It's just a nice little resource. Hopefully you have it all established in your notes, but in our book, one place where you could find all of it. Okay, so last problem, and again, using this. Let's say, actually, let's go back to this problem and realize what I just showed you is an alternative. I started you off with this problem and showed you, and I still think this is the better way. Use the right triangle. The right triangle is used so often in this class and so many others, so I think it's a much better habit to get into. But let's point out an alternative. Given cosine of theta is 5/6, let's find the other trig functions at theta. I'm just abbreviating a little bit here, but I said the whole thing. Given cosine of theta is 5/6, still remember theta is an acute angle. Let's find the remaining trig functions at theta. Let's get our exact answers only. I like the right triangle, but remember, as long as we have both sine and cosine, we could just use those properties to get the remaining trig functions. This identity can get us there. I don't know what sine is, but I know cosine is 5/6, so cosine squared becomes 5/6 quantity squared. That equals 1. Let's solve for sine. And I know this bugs people because it's a trig function, but if you really want, make it an x squared. And at the end, just remember x represents sine theta. How do you solve for x squared? Well, first, let's make that 25 over 36. Subtract that from both sides. So a little fractional work. 1 would be 36 over 36. 36 minus 25 is 11. over 36, but that's sine squared, square root of the whole thing, which you can break down into separately the square root of the top, which doesn't break down, square root of 11 is as good as it gets, square root of the bottom, which the square root of 36 is a clean 6. Now you've got cosine and sine. Notice we had both here, but now instead of just using opposite over adjacent and then the flips, I'd have to do tangent as sine over cosine. And again, just clean habits, good habits, clean up that fraction. And then now we're in the exact same spot. Now it's just the flips. Cosecant, flipping sine, secant, flipping cosine, and cotangent. And cotangent, flipping tangent. So just to point out, sometimes they try and say, use a Pythagorean identity to try and force you to use this idea. But to be quite honest, that technically is using a Pythagorean identity here. We use Pythagorean Theorem, and that is an identity. So no matter which way they phrase that, they're both equally good. Like I just said, I think the right triangle is a little more beneficial because we're just really need to establish those properties, and it's such a good back and forth to get used to. Okay, part 2, a little more calculators and a couple of examples, seeing how we can do this with how there are word problems that we can apply these right triangle ideas to.